So, the image that you see behind me, is it familiar? It's an image of an ultrasound of a human heart. Look at the valves. They are opening and closing in turn, creating the heartbeat sound that you are so familiar with, and it allows us to track the actual heartbeat of the trace that you tend to see when we look at the human heart. But what allows us to create this image? This is ultrasound. Okay, so ultrasound is the use of sound wave and its reflective properties on certain types of tissue in the human body to give us a peek into how structures look like and how they move. And ultrasound or sonogram is really important in our field of medical imaging. We have the MRI, magnetic resonance imaging. We have the X-ray and CT scans, and we have the ultrasound. The ultrasound is the least invasive and can be done at almost real time, meaning the image is shown almost instantly, okay, with little to no processing. So in this topic, we are going to look at what is an ultrasound, how to generate and detect ultrasound, and how it's used to actually create these kind of images inside computers. All right, so if you're ready, let's go. First, we need to talk about how to produce ultrasound. And we produce ultrasound by using this device called a piezoelectric transducer, which is the ultrasound one that is often placed on the surface of the skin, okay, to look into the human body structure. And transducer is a device that converts energy from one form to another form. This is how a transducer looks like in real life. You will see that there are different shapes and sizes, and also there are certain types that comes with probes. Okay, so this is to ultrasound smaller organs, or maybe to be placed inside certain parts of the human body to produce a better imaging. The general ones that we are drawing is this type, okay, and it is normally placed on the surface of the skin, like so. When we're scanning, this is the regular ultrasound scan to look into the womb to detect the baby. All right, so to want to see the baby, the ultrasound will enter and reflect off the skull, the tissue, the nose, and that reflective properties will allow us to see the baby. Okay, but since we have different ultrasounds, you can see this probe is kind of small. Okay, the main material that is inside this ultrasound is a type of crystal. Because first we need to produce ultrasound. Now, what is sound? Sound is vibration. Right now, you are hearing the vibration or the movement of the speakers in your laptop or your devices. It is vibrating the air particles. That's why you can hear sound wave. Likewise, this acoustic sound range that you can hear is only within the range of 20 to 20,000 kilohertz. There are sound waves that are above the human's listening threshold, okay, hearing threshold. And this is what we call ultrasound. Any sound above 20 kilohertz. So to create this sound wave, we need to have some device that can vibrate very vigorously at a large frequency. And what is that device? It is a special type of crystal that we place inside this one called the piezoelectric crystal. But first, we need to understand how and what is a piezoelectric crystal. So inside this one, as you can tell, I have shaded blue color. This is the crystal, which is the main character in our discussion in this video. And this crystal is a tetrasilicate unit. So if you're not doing chemistry, that's okay. You just need to know certain properties about this unit. But if you are learning chemistry, then it should be no surprise to you that our Si04 follows the shape of a tetrahedral. A tetrahedral is simply a pyramid, but the base, instead of a square, it's the shape of a triangle. So it looks something like this. But what you need to know, whether you do chemistry or not, is that the oxygen bond, because the oxygen, these are all covalent bonds, okay? So the oxygen side of the covalent bond will be charged partially negative. And to simplify our understanding, we will just call this negatively charged because we're not studying bonding in physics, okay? Whereas the silicon ion is on the positive end of the bond. So the oxygen ion that I guess I will draw in blue would be charged negative, okay? And the silicon ion would be positive. It is a partial charge. It is the distortion of the electron cloud, but this is good enough, lah. Okay, so this is a single quartz molecule or a quartz unit. But now we're going to put many of these quartz units together, and let me show you a 3D drawing of how it would look like. This is a 3-dimensional drawing of your tetrahedral Si04. So once again, the gold one is Si, okay, and all the other gray ones are oxygen. Oxygen, 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 oxygen. But what I want you to notice is on one face, let's say you imagine there's an entire block of this silicon oxide. On the upper face, right, we seem to have a little bit more oxygen than normal because of the alignment or the arrangement due to the shape. So maybe I will highlight this part blue. So you see that all these are negatively charged. So this face is probably going to be leaning towards the negative charge. Okay, so I'm just going to draw a bunch of negative here. Okay, and the bottom face, okay, is where all the gold color silicon is. And this is probably going to lean towards the, okay, I'm going to use red for this. It's going to lean towards the positive charge. Okay, and because the silicon oxide structure allows for one plane, the higher plane, to be positively charged, and sorry, to be negatively charged, and the lower plane to be positively charged. How do we allow this crystal to vibrate at many times? We place alternating current. Because think about it, alternating current is a current source that we can adjust. You have learned the AC chapter, alternating current. You know that alternating current has a certain frequency, and we can tune or adjust that frequency output. So what we'll do is, based on this structure, we will place an alternating, too thick. Okay, so we'll place an alternating current here. And this alternating current will push, stretch, and compress the crystal. Okay, so let's say when this is positive and this is negative, the crystal will be compressed. All right, so we'll be able to compress the crystal when this is positive. No, wait, it will be stretched, sorry, because the positive is attracted. The positive polarity is attracting the negative phase. And down here, the negative polarity is attracting the positive phase. So in this cycle, I guess, time to do some AC review. Okay, so when we place an alternating current inside, let's say this is the positive cycle, the crystal is stretched. So our piezoelectric crystal is stretched. Okay, flip the cycle. Let's say now it's on the negative half cycle. Then this is negative and this is positive. So they will repel. I don't like the negative phase. I don't like the positive phase. From here to here, the crystal is compressed. And because this alternating current has a certain frequency, the crystal will stretch, compress, stretch, compress, stretch, compress, stretch, and compress. Looking a lot like this crystal. So I am unable to find a Si04 GIF of a crystal, but this is also another piezoelectric crystal. This is your zirconium. Okay, don't matter. The idea is the same. When it's stretch and compress, the polarity depends on what polarity you place. You put negative, you stretch. You flip it, you compress. Okay, so they'll be stretching and compressing. It will look something like this as well. When you stretch, it goes to the positive. When you compress, it goes to the negative. Okay, so that will give you an idea. So if we want the crystal to vibrate at a certain frequency of ultrasound, we will place alternating current at the frequency of ultrasound. So there are some form of resonance that is happening. This alternating current, this one here, let's say we assume this is a power supply, okay? This alternating current, if its frequency, the force frequency, is the same as the resonant frequency of this crystal, then you get maximum amplitude resonance. So if the piezoelectric crystal inside the ultrasound one that you place on the skin is resonating, then that would be what we want to create the kind of ultrasound image that we look for. And so now we are going to try to put this in the picture so we can remember how it looks like. Okay, so the 3D diagram is not necessary. I'm going to draw a 2D diagram of the silicon structure now, the silicon lattice structure. So we're going to view this from the top. You put your eye here, you imagine what you see. So if you place your eye from the top, right, you can't, and you take a single layer of silicon, you won't be able to see this oxygen. You'll be able to see this silicon and then these three other oxygen, which means you will get a structure that looks like this, like the base of the pyramid. Okay, so it's a triangle. This this thing here is an entire silicate unit, this triangle dotted line. Okay, so as previously mentioned, you will see that all the oxygens are more or less in, depends on how you cut the crystal, but this crystal is cut in such a way where all the oxygen is facing on the top face and all the silicon is facing on the bottom face. So that means the top face is negatively charged. I've drawn it here. And the bottom face, this part here, sorry lah, the picture a bit, the electrodes already shifted a bit, but I think you get the idea. Down here would be positively charged. Okay, so if in the first case, right, this one is when there is no electric field. So on both sides of the electrode, it is silver coated. Okay, silver coated for better conductivity. And in this first diagram, the first one from your left, this one is when there is no electric field. So that means there is no change in shape. We call this unstressed. I think that is better, like, remember stress and strain? So there's no stress, there's no strain. Okay, so no stress. Now let's say I want to stretch the quartz crystal. So if I want to stretch the quartz crystal, I have to attract, right? So I'm going to attract the top plate, the top part of the crystal with a positive charge here. And then I will attract the bottom part with a negative charge here, meaning I will apply an electric field that is pointed in this direction. This is the direction of electric field. Okay, so if this is the direction of electric field, the negative side will experience an electric force in the opposite direction, and the positive side will experience a force in the same direction as the electric field strength. So you see this E and this FE, same direction because it's on the positive face, and the negative face will be in opposite direction. So in this case, there's electric field, and then your crystal is stretched. Okay, I've colored all the silicons red color. Okay, so from here now, think about compressing. If I want to compress my crystal, the same structure is still there. Up here will still be slightly negative, and down here will still be slightly positive. Okay, so let us just write it down for our brains to brain. Ding, ding, positive, positive, positive. So if we want to now compress, what do you think we should do? We should flip the electric field, right? So we're going to flip the electric field such that here is compressed, so you want to push it away. So in order to push it away, this will be the negative half. Let me change color a bit. Maybe I should use purple. So this is the negative half and this is the positive half. Okay, meaning this one will repel. FE will be in this direction. This one will also repel. FE is in this direction. I guess you could also draw the direction of the electric field. Okay, so FE for negative is opposite direction, positive is the same direction. So we place an alternating electric field inside. So in this case, the crystal is compressed. And if we change these two often enough, the entire crystal will vibrate. And this is how you generate ultrasound. But what do they normally ask you to do? If this diagram, I spend some time talking you through the diagram so that you can remember how to write the essay. So the next part, we're going to write the essay. So this is a fairly common essay question. It came out a few times before. The most recent time where it came out was Winter 17 paper 4.2, I believe. So the answers here are modeled after an older mark scheme. So I will try to incorporate some elements from the older mark scheme and the newer mark scheme to give you a more comprehensive explanation about how ultrasound is generated. All right, so if you're ready, let's go. Number one, describe the setup. If you don't describe the setup, nobody knows what's going on, right? So we're going to describe the setup first. Opposite faces of a quartz crystal. So you can use the word quartz crystal, or you could also call this a piezoelectric crystal. are coated with silver to act as electrodes. So the silver coating itself is your electrodes. Okay. And the second point is a little bit hard to brain, especially if you don't do chemistry, but let us write it down first. Since the center of the positive and negative charge are not coincident or do not coincide, coincide here means not at the same point. Okay, so are not coincident. The potential difference applied across the crystal will cause the crystal to change its shape. Okay, so this is a unique way to talk about the crystal. When I show you the crystal structure just now, it has a very unique pattern. Okay, it looks something like this, right? And because the pattern is very unique, depending on how you cut the crystal, there will be a phase that is negative and there will be a phase that is positive. Okay, so let me explain to you what do they mean by the center of charge being coincident or not coincident. Here I have drawn a green color triangle, okay, to show the center of charge for the silica atom. The silicon atom, the center of charge is a little bit like center of mass to make your life easier. Okay, but the actual situation, right, is such that the orbitals, which is generally in a cloud form, the center of charge of these green orbitals will be in the middle. But to not give ourselves a headache, we'll just draw a triangle. Okay, so the center of charge for this thing is the center of mass in the triangle structure drawn, just to simplify our thinking a bit. Okay, so this is the center of charge for the, center of charge for the positive here. I'm going to repeat again the same procedure, but for the negative charge. All right. So you will see that the blue color triangle is to show the center of charge for the negative charge. And because it's also an equilateral triangle, they kind of like sit on the same place. Because these are equilateral triangles, it's a symmetrical shape. But let's say, for example, you apply a certain tension or a compression and you stretch the crystal. Because it goes both ways. You stretch the crystal, you create current. You apply current, you stretch the crystal. So between tension and compression, you will see that when it's being stretched, the base of this green color triangle, so let me draw the green color triangle for us. This base of the green color triangle is now lower, because there's more there's more positive charge here, lack of electrons. Okay, so the center of the negative charge will be here. Closer to the base, the center of mass of this green color triangle will be closer to the base. Okay, so closer to the base means this is the center of the, sorry, not negative, but positive charge. Closer to the base, this is the center of the positive charge. All right, so if you're always confused about what is center of mass, it's just where the equilibrium point is. For this triangle, equilateral, it will be right in the middle. So for the no stress diagram, they are at the same point because it's right in the middle, two triangles. Whereas for this one, the positive is closer to the base because it's a fat triangle, a short triangle. You can see it here. I mean, right beside my head, it's a short triangle. Okay. Whereas the tall triangle, center of mass is taller. You know this one. It's logic. What? Your taller friends are less stable than your shorter friends. Okay. So this will be positive. So likewise, if let's say I repeat the same drawing, but for the negative charges, whoops, kinda, but hang on, I can draw a better one. Okay, for the negative charges, this is also a distorted triangle, so the negative will be closer to this point. So they don't coincide anymore. So this is what it means by, okay, let me highlight this one. This is what it's meant by not coincident. Okay, so the same thing will happen here as well, because right now we are stretching out the charges. So for the positive charge, the center of positive charge is closer to here because it's a tall triangle. And for the negative charge, my drawing is not very nice, but I think you get the point. The negative charge, the center is here, closer to the top. So once again, not coincident. Whereas this one, they coincide. So you look at the shape. But you could also just memorize the sentence. Center of positive and negative charges are not coincident. Cool. Okay, next point. When we apply potential difference, the silicon will change shape, stretch, compress. We have explained just now. Okay, so now we will say when an alternating, let me change thickness. When alternating potential difference is applied across the crystal will vibrate. Okay, so the crystal is cut specifically so that it vibrates at resonant frequency in the ultrasound range, so above 20 kilohertz. All right, and this happens when the applied AC frequency is equal to the natural frequency of the crystal. So that's why they have to cut the crystal in a specific way. It's not just any good old crystal you find on the ground or in some cave and then you can just ta-da, ultrasound one. All right. So this is how ultrasound is being generated. Number one, you talk about the setup. So I will label the main points here. Make sure you cover the setting, the setup. Okay. And then talk about the properties of the crystal. So the positive and negative charges, the center of charges are not coincident. So potential difference applied across the crystal will cause the crystal to vibrate or change shape, right? So when we place the alternating potential difference, the crystal will vibrate. So just what happens lah. And then down here would be generating ultrasound. All right, here to here, ultrasound. Cool. So this is how ultrasound is generated. And as mentioned just now, if potential difference can change the shape of the ultrasound, then if you change the shape of the ultrasound, it can also create a potential difference. What does that mean? I'm going to bring you back to this diagram again. So you can see that if I'm stressing and compressing or vibrating the crystal, you get a ultrasound. You get a alternating current that we can detect. So an example of this in your daily life is your heating element inside your lighter. So if you have a lighter, there's a tiny crystal here called the piezoelectric element. When you press down, you are compressing the crystal. The crystal will set up an electric field. When the crystal sets up an electric field, the current will flow, and then we will shoot some fuel, some gas there. The gas will light up. Then you can light your birthday candle, light your cigarettes. Do not smoke, it's bad for you. So the whole idea is if I apply alternating current, crystal will change shape. If you make the crystal change shape, you create current. Okay? Apply electric field, changes the shape of crystal. Change shape of crystal, you get electric field. It's a two-way process. Okay? So this drawing perfectly shows it. Okay, so if I stretch, if I apply tension to the crystal, you can see that the positive charges are mainly on top here. This part here is positively charged because the center of positive charge is up here. Okay, so I'm just gonna, so just now positive was red, right? Okay, so this is a positive charge. The center of positive charge is here. Okay, and down here is negative charge because the center of negative charge is down here. So because it's not coincident, when you stretch the crystal, in this case, we stretch the crystal horizontally, we can detect an electric field. So when we set up this electric field, we can measure. Okay, so we just connect this to a voltmeter or a CRO, and then we can measure. This is a very small voltage, so you need a very sensitive voltmeter. All right, same thing when you compress. When we compress, you can see that the center of the negative charge is up here. Okay, and the center of the positive charge is closer to the bottom side. This is positive. So as you stretch, compress, you get to generate your own alternating potential difference. So the idea is you change shape of crystal, you get alternating potential difference or electric field. This one also can. So when the crystal change shape and you get alternating potential difference, this is how we detect ultrasound. When you apply alternating potential difference and the crystal change shape and vibrate and you put the crystal on the belly, this is how you receive or generate ultrasound. Okay, so we will detect ultrasound because there is reflection. Okay, we are using the same one. So what happens now is, let's say we send some ultrasound into the body. Okay, so there are some pictures here just to remind you. But let's say we are sending some ultrasound into the body. Okay, so it's sent into the body, and then there's some reflection happen, and then you receive ultrasound. So the transmitter and receiver are the same thing. The transducer is both transmit and receive ultrasound. Why? Because it's just a piezoelectric crystal. So if I place current into the transmitter, the ultrasound, the piezoelectric crystal vibrate, ultrasound go into the body, reflect, come back, want to detect, piezoelectric crystal vibrate, send to the detector. Okay, normally it's a CRO or a voltmeter or a sensing device. Okay, so all of this, we just call it signal processing, electronics. Okay, so last essay that we're going to write is how to detect this ultrasound. So here is generate. Here is detect. All within the same ultrasound one. Points to include when writing about detection of ultrasound. Okay, so number one, when reflected ultrasound, so where is it reflected? So reflected ultrasound generally is from the human body, okay, or from any structure lah. In physics, we tend to call it structure because we are very impersonal like that. But you can use medium or human body, incidence on the transducer, and the transducer acts like the detector because it's the same thing. So what is inside the transducer? Your good friend, the piezoelectric quartz crystal. So the piezoelectric crystal, what happens? When the ultrasound reaches the crystal will vibrate. So the piezoelectric crystal vibrates, like my alarm vibrated just now, vibrates. Okay, so the piezoelectric crystal, okay, inside transducer vibrates. What does this vibration cause? It will cause a electric field across the crystal. So this vibration generates an alternating potential difference across the faces of the crystal. Okay, so what do we do with this alternating potential difference? We measure. So this PD is picked up and processed. Okay, so generally it's already detected. We will talk about the processing after you have watched a few more, or we have studied a few more subtopics. Watch, study, what is 2020? Okay, so this is how we can detect ultrasound, right? So if you need to, depending on the marks, I may talk about the structure of a transducer. So this is a transducer. Inside a transducer, there's a crystal, okay? When reflected ultrasound from whatever structure hits the crystal inside the transducer, the crystal inside will vibrate, blah, blah, and you get the potential difference. So that's how you detect. Okay, so let's recap. Before we can even think about creating a beautiful ultrasound image to show us all the amazing things, we need to know what's a transducer. Okay, and a transducer is something that converts energy from one form to another. A slightly anomalous past year question also wants you to talk about the users of a transducer. So I'll just include them here. Users of transducer includes microphone. So if you've watched the operational amplifier video, you will understand that we can use a transducer to pick up sound. Okay, you can use it as a pressure sensor because it can stretch and compress. I've shown you the lighter before. And inside your watch, there's also a crystal because the crystal can vibrate. If you're interested, go Google. All right. But what you actually need to know is how we generate ultrasound, which is to apply an alternating electric field such that the crystal vibrate. How to get ultrasound. Why does the crystal vibrate? The center of the positive and negative charges are not coincident. Sorry about that. Okay. And what should we do so that we can create the ultrasound? We will cut the crystal specifically so that the applied alternating current frequency is equal to the natural frequency. So producing ultrasound. Recent years, they have asked about detection of ultrasound, which is the same idea. When the ultrasound hits the transducer send out the ultrasound, transducer also detect the ultrasound that come back. Ultrasound go, reflect, and come back. So it's the same transducer that picks up the signal. Reflected ultrasound will incident on the transducer, which acts as a detector. And then the crystal will vibrate. Then there's a potential difference that we will pick up and process. All right. So how does the processing look like and what happens in the reflection? That would be in the next video. All right. So this video is just writing some essay questions. That's all. See you in the next one. Bye-bye.